Welcome to This Explainer. Today, we're diving into a seriously fascinating intersection of science and technology. We are going to look at how cutting-edge automotive engineering is literally borrowing from human biology and artificial intelligence to completely revolutionize the way our cars handle bumpy roads. If you've ever wondered how the vehicles of tomorrow are going to adapt to the environments around them, well, you are in the exact right place. So buckle up and let's get right into it.
We've all been there, right? You're cruising along, enjoying the drive, and bam, you hit an unexpected pothole. It is a universal annoyance. But if you stop and look at it from an engineering standpoint, it's actually a massive physical challenge. How exactly do you keep a heavy, moving, 2-ton vehicle smooth and stable over totally unpredictable terrain? Historically, we've basically just relied on thick metal springs and fluid-filled dampers. But as we'll see today, that traditional mechanical approach has kind of hit a ceiling.
To ground our explainer today, we're looking at a brand new, comprehensive 2025 academic review from the Journal of Information Systems Engineering and Management. This paper actually proves that the sci-fi concepts we're about to discuss aren't just theoretical anymore. They are already yielding real, peer-reviewed mathematical results in the world of automotive design.
So here's our roadmap for today. First, we'll cover the pothole problem, then nature's shock absorbers, the brains behind the bumps, balancing comfort and control, proving it on the road, and finally, the future of suspension.
Let's start with Section 1, the pothole problem.
Okay, so to really get why we need biology and AI here, we first have to understand the fundamental limitations of traditional rigid suspensions. For decades, traditional suspensions relied purely on this one rigid mathematical relationship. It balances the sprung mass, that's the m, along with a damping coefficient c, and the spring stiffness k, against the external force of the road, which is f of t. The problem? Well, it's completely rigid. A traditional spring doesn't learn, it just blindly reacts. It severely limits adaptability because you simply cannot change those physical properties on the fly when the road surface suddenly changes.
Moving on to Section 2, nature's shock absorbers.
Think about this. What if a car didn't just rely on stiff metal coils? What if it could literally bend its knees and brace for impact exactly like you or I would? Enter the biomechanical model. This is where automotive engineers are using biomimicry to move away from rigid components entirely. Think about how incredibly adaptable the human musculoskeletal system is. When you jump off a step, your brain instantly tells your muscles and tendons to brace, absorb, and distribute that force. Engineers are now designing advanced suspension systems that mimic this exact biological adaptability, adjusting dynamically to road conditions rather than just bouncing over them.
Which brings us to Section 3, the brains behind the bumps.
Now, muscles are pretty useless without a brain to command them, right? A dynamic suspension needs real-time intelligence to act as the vehicle's digital nervous system. To do this, engineers are deploying a highly specific AI toolkit. They use convolutional neural networks to act as the car's eyes and touch, processing just massive amounts of sensor data. Then, multitask deep belief networks step in to handle the complex patterns in the suspension behavior. And this is brilliant. They integrate hybrid fuzzy logic with bio-inspired algorithms like particle swarm optimization. This essentially mimics how a flock of birds instantly reacts and adapts together, allowing the system to tune the car's suspension parameters in real time.
What this all boils down to is a core shift in the technology. We are literally mimicking human reflexes. These neural networks synthesize all that complex data so the car doesn't just take a hit and react after the fact. It actually anticipates the bump. By learning from historical performance data, the AI predicts the optimal damping characteristics needed before the full force of the impact even has a chance to travel through the chassis.
Next up, Section 4, balancing comfort and control.
Of course, predicting a bump is amazing, but it kicks off an inherent engineering tug-of-war. On one side, you have ride comfort. Scientifically, this is measured by the root mean square, or RMS, acceleration experienced by the passengers. You obviously want this to be plush and soft. But pulling hard on the exact opposite side, you have handling stability, which is assessed through the dynamic load coefficient. This requires stiffness to keep those tires safely glued to the asphalt. It's a tricky balance. Make a car too soft and it handles terribly. Make it too stiff and your passengers are going to feel every single pebble.
So how does AI actually solve this dilemma? Well, multi-objective optimization frameworks act as the ultimate referee. The research highlights algorithms like the Non-Dominated Sorting Genetic Algorithm 2, or NSGA2 for short, alongside Bayesian optimization. These algorithms act kind of like a grandmaster chess player. They look dozens of steps ahead to manage these directly competing objectives simultaneously, finding the absolute perfect sweet spot between a comfortable ride and total handling control, all in real time.
And honestly, the results are pretty mind-blowing. Studies within this review show that these multi-objective optimization approaches can achieve up to a 30% improvement in ride comfort. That is a massive leap in physical comfort for passengers, and it's achieved simply by letting algorithms find design solutions that might actually seem totally counterintuitive to traditional engineering.
Now, as you can probably guess, calculating all this on the fly takes immense computing power. That's why engineers use something called surrogate-assisted optimization. Think of this as the AI doing mental practice. Instead of running incredibly expensive and slow full-system physical simulations for every tiny little tweak, they use artificial neural networks to approximate the complex equations. And these surrogate models are good. They can achieve greater than 95% accuracy in representing the design space.
And the real kicker here is speed. Surrogate-assisted optimization isn't just smart, it's incredibly fast. It reduces development time by up to 60%. This lets engineers computationally test countless scenarios and explore innovative suspension concepts that would have been completely overlooked using traditional, slower methods.
All right, Section 5, proving it on the road. Because theory is just theory until the rubber actually meets the road, right? Taking a suspension system from a line of AI code to a physical car takes a rigorous validation pipeline. First, they use multi-body dynamics computer modeling, specifically high-fidelity, multi-flexible body dynamics, to capture complex stress distributions. Second, they move to controlled component-level lab testing, using force plates and motion capture. Finally, the big test, human subject road trials. This is where they correlate that objective mathematical data with subjective, human-perceived comfort.
And the hard data absolutely anchors these tests. The paper confirms that these validated, optimized models show normalized root mean square error, or NRSME, improvements ranging from 0.79% to over 7%. Now, in the super strict tolerances of automotive engineering, that is a mathematically massive victory over traditional setups. It proves beyond a doubt that this biological, AI-driven approach is objectively superior at isolating vibrations.
Finally, Section 6, the future of suspension.
So where on earth do we go from here? The research outlines some truly incredible concepts that are currently in development. We are looking at real-time quantum computing to process these optimization algorithms instantaneously. There are also really cool sustainability efforts focusing on energy harvesting, literally capturing the kinetic energy from road vibrations to help power the car. We're also going to see the integration of connected vehicle technology, where vehicles are constantly communicating with each other and the infrastructure around them. And lastly, the development of advanced sensor networks that perfectly mimic nuanced biological sensory systems.
Which leaves us with this final thought. We've gone from rigid metal coils to AI systems that mimic human muscles. What happens when your car uses quantum computing and infrastructure communication to essentially talk to the road, perfectly bracing its biologically inspired suspension before the tires even touch the bump? The future of driving isn't just about what powers the car, it's about the digital nervous system that connects it to the journey ahead. Thanks for joining me on this explainer, and keep learning.